Hello, we're continuing our video lecture series on Chapter 6.1, the Log 5 textbook. And we're going through an example in the end of the last video about what values of proportion and sample size can we assume the distribution of sample proportions is normal. So we looked at sample size of 1 and p equals 0.5. We can't use normal distribution because we don't have that at least 10 successes and 10 failures. With 20 and 0.5, we could use the normal distribution because n times p is 10, so 10 successes, and n times 1 minus p, in this case, is also 10. So as long as we have 10 or more, we're good. And then we also looked at if n equals 20, sample size of 20, with a proportion of 0.9. We have plenty of successes, 18 successes, which is good, but the number of failures is less than 10, so we can't use normal distribution. So notice here sample size alone is not good enough. We have to connect that with the proportion. So if we have a sample size of 100 and a proportion of 0.9, here we would have the successes equals NP, and that would be 100 times 0.9, which we would have 90. So we're good there. Have at least 10. And the number of failures would be n times 1 minus p, which in this case is 100 times 1 minus 0.9. And 1 minus 0.9 is 10%. 10% of 100 is 10. So we can use normal distribution. Because I've got at least 10 successes, 90, and at least 10 failures. So if we look at stat key, again, our proportion here is at 90%. With sample size of 20, we did not get a normal distribution. With a sample size of 100, I generate a whole bunch of samples. And I'd still say there's a very slight left skew over here. But we're going to use that normal distribution to approximate. We're going to be able to say, oh, we can approximate this distribution with that bell-shaped, ghost-shaped curve. And lastly here, if we take sample size of 30 and population proportion of 0.6, successes is NP, that's 30 times 0.6. Which is 24, 18. So we have plenty of successes, and we're going to make sure we have at least 10 failures, n times 1 minus p, which in this case would be 30 times 0.4, and that would give us 12. So again, we can use normal distribution in this case, as long as I have 10 successes and 10 failures. And to visualize that, if we go to stat key, let's make that sample size at 30, edit proportion to a 0.6. And if we generate a whole bunch of samples, notice we get not a perfect normal curve, normal distribution, but we're going to use a normal curve to approximate this. Okay. So reviewing again, that's the make sure we have at least 10 successes and 10 failures, and then we can go to normal distribution. So that's the if n is sufficiently large. This notation is saying the sample distributions of p-hats, of sample proportions, we could assume is normal, where the center is p, and then the standard error is the square root of p times 1 minus p over n. And this is a good approximation. Normal distribution, as long as we have those 10 successes and 10 failures. Okay, so that's good, but the standard error formula, you might have realized we have a problem. We're trying to estimate p hat, and we're going to use the standard error. Oftentimes, we don't know what p is. So if we don't know what p is, one solution is to substitute p hat, our best estimate, into this formula. And we're going to use that when we construct confidence intervals. So here again we have the confidence interval formula from chapter 5. we take our statistic plus or minus z star times the standard error. So for a single proportion, so long as n is large enough for the number of successes and the number of failures to be 10 or more, then we're going to use the formula to compute a confidence interval to be p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. So roughly the same formula, but a little bit more specific for looking at a single proportion, so long as there's the 10 successes and 10 failures. All right, so March 2011, a random sample of 1,000 US adults were asked, do you favor or oppose sin taxes on soda and junk food? And this was all US. In 2011, I was living in Washington State, and actually the state Senate proposed, or the legislation proposed a bill to increase taxes on, it was soda and junk food, I think fast food as well. We'll go through this example and I'll let you know how that bill fared in the election when I was in Washington. So out of that 1,000 US adults, 320 responded in favor of the sin tax. So let's construct a 95% confidence interval for the proportion of all US adults that favor these sin taxes. I first want to note the counts are greater in each category. Check. Okay, what does that mean? Let's go back again. We're going to have the 10 successes and 10 failures. 320 adults responded in favor of the sin tax. So I could multiply proportions like I did on the previous examples, but this is telling us the number of successes. 320 were in favor, and then how many were failures, were not in favor of sin taxes? Well, it's out of 1,000, so you had about 680. So the counts are greater because they're both over 300 in each category. So that means when we construct a confidence interval, we could use the normal curve of z star. And don't forget that z star for 95% is 1.96. And you, of course, could write that down. Or you always have access to StatKey. Click on the normal curve. Make sure the mean is down and your deviation says 0. Click on two-tail so that middle says 95%. And right here, there you get your z star, 1.96. All right, we got the formula, p hat plus or minus z star times the square root of the sample proportion times the opposite of the sample proportion over n. And before we go over, we have, what is that p hat? P hat is 320 divided by 1,000. So we have 0.32, that's 320 over 1,000, plus or minus 1.96 times the square root of 0.32 times 1 minus 0.32 over 1,000. Throw that in your calculator. Here, this is the standard error. We get 0.015. Multiply that times the z star, 1.96. And then add and subtract that to 0.32 to get the confidence interval of 0.291 to 0.349. So as an interpretation, we'd say we are 95% confident that between 29.1% and 34.9% of US adults favor sin taxes on soda and junk food. All right, and in 2011 or 2012, I forget the date, when the state of Washington put a bill on the ballot to increase taxes on soda, junk food, and fast food, it failed miserably. I think it only got about 39% approval. So it was, 60+% were opposed it. So the taxes were not increased. So that fell in line with this national percentage average. I wonder if that has changed in the last 6 years. I don't know. All right, just to note right here, you have this confidence interval using the formulas. And again, if we go back to StatKey, we could have done this in chapter 3, without the formulas, the confidence interval for a single proportion. Click on edit data, and we had 320 over 1,000. Click OK. And if you generate a couple thousand, click on two tail, make sure that middle says 95%. Notice down here in chapter 3, this is how we construct the confidence interval, 0.292 to 0.349, 0.291, 0.349, so not the exact same, but very close. It's a good approximation. Keep in mind in chapter 6, for the homework and quizzes and the video lessons, I want you to use this formula, not the bootstrapping. I'm just showing that to see that this matches up pretty closely with what we did earlier in the semester. All right, here's just another randomized distribution. And again, the confidence interval is slightly different, but very close. Okay, so one new topic in chapter 6 we're going to get at is what about that margin of error and coming up with the margin of error. So suppose you can choose your sample size if you know a specific margin of error that you want. So we have this margin of error formula, and given this formula, we could solve for n to get this right here. N is z star over the margin of error squared times p hat times 1 minus p hat. So you could use this formula and have this formula. I want to go through once just to show you, okay, where did that formula come from? All right, here, so we've got the confidence interval for p hat plus or minus z times the standard error, which is given right here. And don't forget, in general, confidence interval is always your point estimate plus or minus margin of error. So margin of error equals z star times the square root of n times p hat times 1 minus p hat. So what we're doing right now is solving for n. If I wanted to solve for n, the first thing I would do algebraically is let's divide both sides by the z star. So we get the margin of error divided by z star. And that's going to equal the square root. Just copy this over. So if I'm solving for n, first step is divide by z star on both sides. And now if you remember, if we want to get rid of a square root, remember what we do on both sides of the equations is square. So we're going to get the margin of error over z star squared. The square root and the square cancel out. I'm just left with p hat times 1 minus p hat. Just going through a little bit of algebra here. And now what I could do with this, we don't need the middleman anymore. I'm going to just delete this. And now here we could cross multiply, or if I have two ratios that are equal to each other, I could invert these. In other words, I could write this as, instead of margin of error over z star over margin of error, and that's going to equal n over p hat, over p hat times 1 minus p hat. And then lastly, I can multiply both sides times p hat times 1 minus p hat. I need to make sure to do that on both sides. Whoops. And if we remember, when you do that, then we could then cross out the numerator and denominator. Those cancel out. And n is going to equal z star over margin of error squared times p hat times 1 minus p hat. So I want to go through that once. I won't have you do that, but we're just taking that margin of error formula and solving for n to get this formula. Right here. All right, and then in the next video, we're going to go through how to use and analyze this formula to come up with